Welcome to the new way of learning stuff. This is your chemisode video. It's the first episode in your Year 11 career of chemistry, and it's going to introduce you to how we're going to do these things. I've already ran through this in class, this information, and this is just for your reference over the holidays for you to do your holiday homework. But in the future, these chemisodes are going to be what you watch before you come to class. This one is entitled The History of Chemistry, from Cavemen to Quantum Mechanics. And it's going to run through what the history of chemistry is all about, how it came about, where it came from, and it's more so the history of atomic theory rather than the history of chemistry, but those two things are one and the same really, because without the atomic theory, we have no idea about chemistry itself. So, how did chemistry come about? Let's have a look at it. The first chemists were the cavemen. Really early on, what people used to do was eat meat. Right? Cavemen hunted, they were men, they were brilliant, they went around, they killed things, and they ate them. Right? They survived that way. What they did is, after a while, they found fire. And they realized that if we put the meat on the fire, it changes some way. And it's better to eat when you cook it. So along came the idea of fire and cooking. Chemistry is glorified cooking. A nice physicist named Shannon Nash told me that chemistry is just glorified cooking, and it is. Science in cooking is chemistry. What you're doing is changing one thing into something that's a little bit better, and that's chemistry. So the cavemen, because they were cooking meat, were the first chemists ever. They didn't really get the chemistry behind it. They didn't understand why it changed or how it changed. They just understood that cooking it made it better. And they told their kids, and their kids told their kids, and passed on through generations on how to cook their meat. And they had the understanding of how the meat changed and was better to eat. Fire is a very useful tool in chemistry, and a lot of experiments were done with fire. Cavemen realized what was needed for fire. Obviously, you needed oxygen, or they needed air. They didn't know what about oxygen, they needed air. And the more air they gave the fire, the hotter it got. After a while, what they might have realized, or generations and centuries and thousands of years later, people realized they could get really hot flames, and if they put certain types of rocks into the flame, into the fire, when that fire died out, they were left with a shiny piece of red metal. And that red metal was copper, because the rock that we're using was a copper ore. And if you heat a copper ore, what can happen is it becomes reduced and you get pure copper from it. They realized that you can shape this copper. If you heat it up again, it melts and you can mold it into the shapes that you want it to be. And you know what shapes they used? The first shapes they made with copper? Spears. Spears to kill animals to make more meat, and spears to kill people so they could take over their countries. So we understand the Copper Age and the Bronze Age came out of turning rocks with fire into copper. This is chemistry. All right? It's not chemistry yet, but it has the bare bones of chemistry, turning one thing, a copper ore, a rock, into pure copper itself. So you have the bare bones of copper, changing something into something else. Bare bones of chemistry, sorry. They didn't write this down, they didn't know how it worked, but they knew it worked, so what they did, passed it on to their kids, passed it on to their kids, passed it on to their kids. They didn't understand the science behind it, but they understood that it worked, so that was fine. A few more centuries down the line, we have the ability to make a hotter fire again, adding more oxygen to the fire. You get temperatures in excess of 3,000 degrees. What happens? You get a different type of rock, and that will be able to be turned into iron. So you get to the smelting of iron, where you're turning iron ore, okay, into pure iron. And once again, what did they do with the iron? They made swords. Okay, it was harder than copper, so they could kill all those people who had copper swords, all right, and bronze swords. So therefore, Iron Age came about. We have the Iron Age. Once again, they didn't know what happened. They didn't understand the science behind it. They didn't write down their theories of how to make iron. They just passed it on through generations of how to make iron. But they didn't understand the science behind it. They just knew that you could turn the rock or the ore into a metal. And that was brilliant for them. Around about the 1600s, you got this surge in the amount of alchemy that was happening. All this stuff that I've been talking about is known as alchemy, where it's not a research thing. Nothing's been written down, nothing's been experimented on. It's just simply doing something for a fit purpose. Alchemy is really a poor man's chemistry, where you're just chucking stuff together and seeing what happens. All right. Alchemy around the 16th century was around about where they looked for the search for the philosopher's stone. The philosopher's stone was a mythical object that can turn anything into gold. Okay. They believed, the alchemists, that there was a thing called the philosopher's stone that had the ability to turn something into gold, because they've seen ores turn into metals, and that because they've seen people make wine out of grapes, and people make beer out of hops and some wheat. They thought, there must be something that we can turn into gold. So they went around and tried to search for the philosopher's stone, chucking a whole bunch of things together. Because there was a search for the gold's a very, very expensive thing. What they didn't want to do is have anyone else know their knowledge. So they tried to keep it really close to their chest. They didn't want to write things down and help everyone out, because if they help someone out, they might get all the glory, they might be able to get all the gold. So the alchemists were very, very secretive, and so therefore not a lot progressed with that idea. Nothing was written down, nothing was explained. There was no collaboration with our alchemy. So we had an issue with that. Another issue might have been the idea of witchcraft, that if you're doing something which is turning something into something else, you're a witch, so they burned you. So therefore we have no progression in our understanding of chemistry. So how did alchemy go into chemistry? How did alchemy turn into chemistry? The big idea is we write things down. We help each other out. We work collaboratively. Okay? Alchemy, no idea, no writing things down, no understanding of how things work. With chemistry, we have writing things down, we have helping each other out, and we have a search for the understanding of what things are made up of. Understanding what things are made up of will help us understand how things behave, and therefore we can understand why there is no such thing as the philosopher's stone, why there is no ability to turn anything we want into gold. There's a reason, and the reason is to do with what things are made up of. So a lot of time and effort now, instead of just chucking stuff together, is using scientific method, having a set aim for an experiment, having a hypothesis, what you think is going to happen, testing your hypothesis, working out if it's correct or not, and then writing a report based around what you thought would happen in your experiment. That way, the person who's coming along after you're dead can look at your experiment and go, that didn't work, I'll try something different, rather than trying and making the same mistakes time and time again. We're writing things down, we're understanding how things work. And that was the birth of chemistry, where that started to happen. Set experiments with records made of these experiments so people can learn in the future. The next part of this is about the history of the atom and how one theory of atoms and atomic theory was born and how it changed and got developed to where it is now. And we're going to look at that now. So we have understanding what things are made up of. This is where the atomic theory first began. Started off with defining what we think make things up. Okay? Defining elements. An element is defined as the fundamental building blocks of all matter. Basically, it's what makes up everything around us. And believe it or not, it started back in ancient Greece, where we had two people, Aristotle and Democritus, kind of going at it with a bit of an argument of what they believe makes up the world around us. This person, Aristotle, believed that everything around us was made up of fire, air, water, and earth. 4 elements, and that there was no way to divide them into a particle of fire, a particle of air. It was all continuous. Okay? That's Aristotle. Fire, air, water, earth. Democritus, on the other hand, here, he believed in the idea that everything around us is made up of tiny building blocks called atomos, which means indivisible particle. He was the idea that came up with, said that if I get a piece of paper and I rip the paper in half, then I rip it in half again, I keep on ripping it in half, okay, I'll get to a point where I cannot rip that paper in half anymore. And that is where we get the idea of atoms from. As scientists, as chemistry students, we understand which one's correct. Democritus is correct. However, Aristotle at the time had a big, he was kind of higher up in the social scene. He was a bit of more of a outgoing person. He had a really good friend who was very high up at the time. And he told this friend that, I think I'm correct and Democritus is wrong. So the person who was higher up kind of got the word out and said, you need to crush Democritus' theory, we don't believe it. And he goes, yeah, fair enough, that makes sense, but why are you correct? And Aristotle said, I'm correct because I have an experiment. And what he did, he set fire to a log. Okay, he chopped down a tree, got a piece of wood, chucked it on the fire and say, look at this. This log is made up of my 4 elements. Fire, air, water, earth. And you can see it. Have a look how it's catching fire. It's burning, so therefore there's fire in there. Okay? Have a look at the smoke it's creating. The smoke, that proves that there's air making up this piece of wood. The tree was a bit young and it was a green tree, so what happened is when it started burning, the sap from the tree started to leak out. And what he says is like, look there. There's water in this tree. So I've got fire, air, water in that tree. And once the fire died down, what was left but ash? The ash, he said, now that's the earth that is in this tree. And so Aristotle, with a very simple experiment, has proven his fact that this tree is made up of these 4 things. It's made up of air, fire, water, and earth. And I was like, well, fair enough, good point, Aristotle there. You've done well. Democritus, prove your point. Prove your point that everything's made up of atoms. However, Democritus couldn't. He couldn't get to the point where he would chop the wood in half enough to say that it is no longer wood. Every time he cut it, it was still wood. There wasn't a point where Democritus could change the wood so it cannot be cut anymore. So therefore, Aristotle was taken as being correct. It's taken as being correct for a good few thousand years. And basically we ended up with, well, not much progression in chemistry since Aristotle's time. Until about the 1600s, when we have our idea of the atom starting to take form. So the first birth of it was Democritus, but it was squished because Aristotle proved he was correct and he had this idea. Moving on to where we are now. The next part is a guy called John Dalton. John Dalton came along and he had a lot of experimental data from people before him. He had people like Priestley and Lavoisier that had done a lot of experiments with oxygen and metals and metal oxides and looking at the weights of these metal oxides compared to the weights of the metals. He looked at the idea that when you make a compound, it always comes up with the same ratio of mass. For instance, if we look at copper and copper oxide, if you take 10 grams of copper, you'll always get 12.1 grams of copper oxide. Okay? Every time you burn 10 grams of copper, you get 12.1 grams of copper oxide. If you take 9.36 grams of copper, what will happen? You end up with 11.37 grams of copper oxide. Okay? 25 grams of copper, 30.37 grams of copper oxide. Again, another example, 6.25, 7.59 grams. What this has found out, what John Dalton really came about with, is that you always get a constant ratio of, if you have 1 of copper, you get 1.21 of copper oxide. You get a constant ratio here. It'll always go up by the same amount. So what he came up with was this idea, that because they arrange themselves in a set order, atoms must be made of tiny indivisible particles that can be combined in set proportions to form compounds. And his idea of an atom was circles. He represented these atoms as circles and as little spheres of indivisible particles. And that when you combine them together, you get compounds. For instance, the alcohol there you can see has got carbon and oxygen, and it's got a hydrogen there, but you can't really see it as well. But these combine together to form these things. And they always come together in set proportions. So John Dalton, through looking at constant mass and the experimental data that was available to him from Lavoisier and Priestley, worked on the idea that we have indivisible particles which we represent as a solid sphere, and that these combine together to form compounds. That was Dalton. The next person in our thing was J.J. Thomson. J.J. Thompson worked with cathode ray tubes. And I've got a young man here with some nice safety goggles and a beautiful periodic table behind him. Going to explain to you about this cathode ray tube. He's going to show you, I'm going to talk to you about it. And I've got this from this guy's YouTube collection. So, looking at this is a cathode ray tube. What we have is a tube which is pretty much depressurized. It's got about 0.0001 atmospheres, no, 0.0001 millimeters of mercury in there of pressure. You've got a metal on one side, a metal on the other side, and you have an inert gas in the middle, whether it be neon, whether it be hydrogen, helium, whatever it is. Not hydrogen, it's not inert. Anyway, what he's done is he's connected this up to a battery, and he's going to put a charge through here. He's going to put electricity through this cathode ray tube. Positive here, negative here, whatever it will be. And it's going to look at what happens within this pressurized or depressurized cylinder. When he flips it on, you get this beam of light coming out from it. Okay? As soon as you flick it on, as soon as you get electricity pumping, you get this beam of light. Let's have a look at what happens to this beam of light when you do a few little simple experiments to it. What our demonstrator here is going to do is going to grab a magnet, a bar magnet. He's going to put a magnetic field around our cathode ray tube. When he puts the magnetic field to it, you can see what happens to our light here. Our light bends. Okay? So because he's put this next to it, our light bends. A negative charge here, the light bends. If he turns it around to show the positive, the light bends towards the positive. Okay? From this experiment, I'll just go here. From this experiment, what J.J. Thomson said is because this light bends in the presence of charge, we must have charged particles in our atoms. So because the light bent towards the positive end, what he said is this light must be made up of those negative areas of atoms. That this stream of light here is your negative particle, and that because atoms are neutral, there must be a positive there to balance that out. So here's his idea. Atoms contain negative particles and therefore must also contain a positive charge. His model of the atom, because he was a nice Englishman, was the plum pudding model. This, where we have an overall positive sphere, solid sphere, and we have negative particles embedded within that solid sphere. And this is known, as I said, as the plum pudding model. And he did this by looking at the cathode ray tube here, the CRT. You also might know old school TVs, not the flat screen ones, the big ones are called CRT, or TVs, or the big monitors, not the flat screen monitors, the computer monitors are also called CRT, which are known as cathode ray tubes, because we have this cathode ray tube emitting electrons, which are giving us the image that we see. So YouTube, because old TVs were made of cathode ray tubes as well. But that's just a sideline. J.J. Thomson, cathode ray tube experiment, found there were negative particles and therefore must be also positive particles there. We have a plum pudding model of the atom from J.J. Thomson. Moving on to our next person. He found the electron and the proton. Moving on to Mr. Rutherford. Rutherford did an experiment using radioactivity. He realized that if you put a radioactive source, you can get a stream of positively charged particles. This work came from a lady named Marie Curie and some other people who worked with radiation, and they found out that this radioactive source emits particles called alpha rays. These positively charged particles are called alpha rays, and they get shot out in a certain direction. Here we have a detector. All right. What happens is these positive particles get detected by the detector. All right. So simple ray of positive particles, alpha rays, and they get hit in this detector here. What Rutherford did was took a bit of gold foil and he placed it in the path of these rays. What he found out was pretty much all of these alpha particles went straight through the gold foil. A very few got changed in direction, and even less bounced back and bounced off. Okay, so here's the experiment. Alpha rays coming from a radioactive source over left of screen, coming straight through a piece of gold foil. This gold foil is about 0.0006 centimeters, I think. Can't remember. Very, very small anyway. Close to like a couple of nanometers anyway. And his alpha rays went straight through. From this experiment, he kind of concluded an idea about what the atom looks like. He concluded this idea, that we have a small positive charge in the middle, very, very small central positive charge. It must be positive because when a particle hits this positive charge, it bounces off. If this was negative, the positive will hit it and it will stay onto it. But because it's positive, it bounces off. So all the positive charge is in the middle here. And that around this positive charge, there is a sphere of electrons. We have the nucleus and we have the electrons around our atom. He concluded that pretty much all of the atom is empty space, that the mass of the atom is in the central nucleus, the electrons are orbiting the nucleus, and that most of the atom is empty space. And he had this idea of the solar system, or the nuclear atom, because alpha rays went straight through the gold foil. So therefore, you have this idea that we have a central nucleus, which is absolutely tiny compared to the radius of our overall atom. I think it was 1 in every 20,000 actually got reflected back. I can't remember the exact numbers, but that was his model of the atom. And because radioactive, alpha particles coming out, you get that idea. So that was Ernest Rutherford. All the mass is in a central nucleus. The most of the atom is empty space, allowing stuff to pass through it, allowing the alpha rays to pass through it. All right, our next man is Niels Bohr, or Niels Bohr. And Niels Bohr he actually worked with Rutherford. I can't remember exactly how he worked with him, whether it was Rutherford was teaching Bohr or Bohr was teaching Rutherford, but they worked at the same time, they lived at the same time, so they did a lot of work together. Bohr built on Rutherford's theory, and he said, yes, I believe that the nucleus is the center of the atom and that most of it is empty space. However, I believe that there's some more ordered structure to where these electrons are. And he looked at and observed the fact that different metals come up with different colors if you set fire to them or you heat them up. And you've probably done this experiment before where you've looked at the flame tests and you put a whole bunch of different salts into fire and you get different colors coming out of that fire. He looked at this and had the idea that these colors must come from changes in energy. And he had the idea that the energy is where the electrons are, and the energy comes out from electrons moving to a higher energy level. From this, he had the idea of the orbital, their shells. So this idea here. And he had the idea that electrons occupy set energy levels. So this energy level here is occupied by electron. Electrons cannot exist in between these shells. They have to exist here or they have to exist here. That's what electrons are defined as by Bohr. He said that this colour comes from the fact that these electrons absorb energy and jump to a higher level of energy. They skip up a shell when they are heated. When they cool down, the electron comes back down to its ground state here. And when it comes back down to the ground state, the energy that it did have in the top part here is released as light. So we see the energy released as light from the electron jumping back down to the ground state. His theory of shells, having 2 in the first shell, 8 in the second shell, and 18 in the third shell, came about from observing the emission spectra from hydrogen. Okay, he looked at how hydrogen, the light that comes off hydrogen, and he looked at it and he said, my model fits the spectrum for hydrogen. And he said that electrons must occupy set energy levels known as shells. His idea worked really well for hydrogen, however, it didn't actually work really well for any of these other metals, which is a bit sad for Bohr. But he had a really good idea and he's paved the way for the next person. He also was a mad gambler and he came up with the idea of this shell theory by looking at horses running around a racetrack. And that's where he came up with the idea of where it came from, having this racetrack around here and horses running in their own lanes. And so that's Bohr and his electron shells. The theory that we have electrons sitting in set energy levels and they can only occupy these set energy levels. If they get more energy, they jump up to another energy level. They remove that energy, they fall down, and we get light coming out of them. It only works for hydrogen, not other elements, and so a new model was needed. And the person who did that was discrete wavelengths being emitted from these electrons. And it's a probability formula known as quantum mechanics. And his quantum mechanics theory and mathematical formulas came up with the idea of subshells and orbitals, and the fact that we have not just a solid electron or a little ball like an electron, that we have an electron cloud, a probability of negative charge being somewhere around our element, our atom. This cloud, represented here by blue dots, every blue dot represents a probability that an electron will appear in a set region. The more blue dots, the greater the probability that the electron will exist there. So therefore we have this idea of an electron cloud. It's very, very hard to explain. This is not his formula. This is just a formula I found while typing in quantum mechanics. I don't even know what this actually means, but it gives you the idea that we're dealing with some really, really complex mathematics. And his idea is complex mathematical modeling of atomic behavior has led to the idea that electrons move in regions of space called orbitals. Electron clouds are created by mapping the probability of electrons existing somewhere around the nucleus. That was Schrodinger, maths genius, the theorizer of quantum mechanics. If you ever want to look at want to see a problem, look at Schrodinger's cat. It's an interesting problem. I won't discuss it here at all, but Schrodinger's cat is an idea about two things having equal probability, therefore being both true, unless you can see one being true on the other one. Anyway, getting distracted here. Moving on. Schrodinger, maths. Loved it. Next person we have is Chadwick, and Chadwick was a guy who found Chadwick was the guy who found the neutron, and I've actually got a little video here showing you exactly how he did that. This is from Tutor Vista. It's just taken from their YouTube channel, so I hope they don't mind me using it here. Anyway, here it is. Chadwick and discovery of the neutron.
Discovery of neutrons. According to Rutherford, the nucleus of an atom contained only protons, and these protons decided the mass of an atom. But we know that hydrogen has one proton in its nucleus, whereas helium has two protons. If the protons were the only particles in the nucleus, then a helium nucleus would have 2 protons and therefore only twice the mass of hydrogen. However, it actually has 4 times the mass of hydrogen. This suggests that there is some other type of neutral particle present inside the nucleus along with the protons. This mystery was put to rest when James Chadwick discovered neutrons in 1932. Let us now understand the experiment performed by Chadwick with the help of a flowchart. He placed a source of polonium in an evacuated chamber. In front of the polonium source, a thin foil of beryllium was placed. The alpha rays were made to hit the foil of beryllium. The beryllium foil emitted the mysterious neutral rays. Chadwick placed a target in the path of these rays. These rays knocked out atoms from the target. These atoms, which had become charged as a result of collisions, were made to enter a chamber filled with gas. These charged particles ionized the gas, and the ions drifted towards an electrode, constituting a current. By measuring the current, he estimated the speed of the ejected atoms and came to the conclusion that the mysterious rays contained particles having mass almost equal to that of the protons. Chadwick identified these uncharged particles as neutrons.
And so there you have the idea that Chadwick came up with to identify and visualize the neutron. The issue with this is, I'll just go through some things that you need to know about. Neutron wasn't found until a good 60 to 70 years after J.J. Thomson found our electrons and protons. The reason we had such a massive gap between it is because the neutron is neutral. It's have no charge. And you can't detect things with no charge. If you have a positive or negative, you can simply look at how it interacts in an electromagnetic field. However, the neutron isn't affected by magnets or electricity, so therefore it's hard to find, hard to detect. So they had to come up with an idea of how we can actually detect it. And this is his idea here, where it's using this paraffin wax to as a barrier kind of thing. Another thing is, how do we know that the neutron existed even if we couldn't see it? Why was a theory there that we had a neutral particle? The idea was that, if I come back here to the start here, because of the different masses of our different elements, the fact that we knew that if an atom only contained protons, okay, it should have been a lot less in weight than we actually saw it being. So therefore something had to be there to be neutral. So we knew the existence of these neutral particles because of looking at the atomic masses of atoms, but we couldn't detect them because they were neutral and we couldn't see them. And you can't see something that's neutral. But what Chadwick did with his experiment was found out that the nucleus of the atom contains both protons and neutrons, and that they weigh about the same. And that's Chadwick. He discovered the neutron. What a clever man. So that's the end of Chadwick, and now we're going to move on to looking at a summary and trying to sum up what you need to know and who these people were in random succession. So, what you need to know is who these people were. You need to know what they did, what experiment they did, what they found out from that experiment, but also what the model of their atom could not explain. Why was theirs eventually superseded? So, we start off with a model that looks like this, which is Dalton's model of the atom. Just a simple sphere. Okay, he did a lot of work with looking at constant mass. He said that my atoms, they are indivisible particles, just like Democritus said, and that they connect together like Lego blocks to make compounds. Then Thompson came along, and he said, because of my cathode ray tube experiment, your indivisible particle must have smaller particles in it. You must have electrons and protons. And he did this by looking at the cathode ray tube. His model of the atom, however, could not explain the fact that alpha particles went straight through it. So therefore, Rutherford came up with the idea of our nuclear atom, where we have the positive charge located in our central nucleus and the electrons orbiting around it, and that most of it is empty space. And he did this by looking at the gold foil experiment, or the gold leaf experiment, depending on what you want to call it, where most stuff goes straight through it. Most alpha particles, sorry, shouldn't say stuff, goes straight through it. His model of the atom, however, could not explain the fact that you have emission spectra, discrete emission spectra, meaning that we have, for every hydrogen atom, we have exactly the same emission coming off it. Or for every lithium, we always get the same color coming off it. So Bohr came up with the idea of having shells, and that electrons occupying set energy levels within these shells. And thus we have our shell theory. Bohr's model of the atom, however, could not explain the full metal array of different colors, so therefore Schrodinger came along and did some fantastic maths and came up with the quantum mechanical version of our atom, where we have subshells and orbitals based around probability of electrons existing. All of these were great, however, none of them could explain the variation in weights for the same element. So what happened is we ended up with Chadwick coming along and discovering the neutron later on with his palladium experiment, dealing with radiation. So we have our people, Dalton, Thompson, Rutherford, Bohr, Schrodinger, and Chadwick. You need to know who they were, what they did, what they found, and perhaps what it could not explain. Even Chadwick's model of the atom has issues. Doesn't explain gravity. Doesn't explain why electrons don't just randomly go into the nucleus. And that's it. That's the end of this podcast. This is a pretty long one. I think it's going to cap out at about 35 to 40 minutes. Watch it in parts, but watch it again. Okay, thank you very much for watching, and please join the Edmodo group, which the group code is seen in the description of this YouTube video. So join that. You'll have a quick little quiz on this, and you'll also be able to get updates of when we have new videos and more quizzes for this topic. So thank you very much for listening, and I'll see you next time.